All right, so here we have an opportunity to practice determining the empirical formula from mass percentage or percent composition. So you see how it says 24.7% carbon, percent hydrogen there, percent chlorine there, right? From that information, we can determine the empirical formula. Do you remember how to do this? Oh, I can't hear you, Fred. No, I still can't hear you.
Can you hear me now?
Yeah, I can hear you. Good.
Okay, yeah. So you take the percentage, because that's grams. When you talk about percent composition, that's grams. So you take your percentage and you convert that to mole, or your grams, sorry, your grams to moles.
Very good. And why do we want moles?
Because you want the empirical formula, and that's just the molar ratio of the different elements.
Very good. So if I want, again, moles of carbon, moles of hydrogen, right? And I want moles of chlorine as well. Let's see, how am I going to get moles of chlorine? Oh yeah, so moles of chlorine, sorry. Let's go back up a little bit there. Okay. I can start with grams of carbon, grams of hydrogen, grams of chlorine, right?
Yep.
All right, so grams per mole, it's 12. So if I take my 24.779, I can divide that by 12 grams of carbon for every mole of carbon. My grams of hydrogen, 2.00794, right? That is my grams of hydrogen, but that's a 1-to-1 ratio for moles of hydrogen, right? Because on the periodic table, that's just 1 gram for every mole of hydrogen. Okay? And then for chlorine, do you remember what it is on the periodic table?
No, I don't.
So 35.45. Okay? So 35.45 grams of chlorine for every 1 mole of chlorine. Very good. So 73.14 is our grams of chlorine. Now tell me why again do I have to, can I go from percent of these elements to just mass?
Well, you can pretend like you have a 100-gram sample, and then those are the grams from that 100-gram sample.
That's right. Very good. Good explanation. Okay, so we put those in our calculator, and hopefully we're seeing that the moles of carbon, 24.77, divided by my 12. All right, can you see that there? That's 2.06. And this one is also 2.07, pretty close. And if I do 73.14 divided by 35.45, 2.06. So now I can take this carbon here, 2.06.
It's just CHCl. It's D.
Oh, you know the answer already? How do you know that?
Because I can see it's a 1-to-1 ratio. They're all the same value.
Okay, very good. And if you couldn't see this, you could just divide this all by the smallest one, which is, like you said, is the same value. Okay, very good. Now, we found the empirical formula. Can we get the molecular formula now?
There's a relationship between the empirical formula and the molecular formula. You just need the multiplier there. And let's see, they gave us the molecular mass. We just need the empirical mass.
Very good. So, if you folks at home know how to do it, then go ahead and take time to do it.
Okay, so we just have to get the empirical formula.
That's right, the empirical formula.
and see how that relates to the molecular formula. Empirical formula CHCl. And we have the same relationship between the empirical mass, yep, and the molecular mass.
Okay, very good. So, empirical mass. Now, how do we get the empirical mass?
You just have to add up the empirical formula. So, carbon, 12, hydrogen, 1, chlorine, 34. What was that, chlorine?
Here, bring up the periodic table, 34.5, or 35.45, 35.45.
Okay, so
I'll add those up here, 35.45 plus the 1 plus the 12. Okay, so we got 48.45. That's our empirical mass. Now what?
well, you got the molecular mass there, 290.8. And so divide that by the 48.45.
All right. And what is this going to give us?
It's going to give us the multiplier.
Yeah, we call it the multiplier, but basically the n equals 6.00 there.
Okay, yeah, so that means that, yeah, 6 there.
That's right, 6 right here. And what is that going to do for me?
Well, C6H6Cl6.
Very good. And looking at these answers that they provided for us, we kind of knew that it had to be either A or E, right? How did we know that?
Oh, yeah, I didn't pay attention to that. But the molecular formula has to be a multiple of the empirical formula.
Very good. Excellent job. Okay, so moving forward. Combustion analysis. Combustion analysis is a way that we can get the empirical formula for a compound by taking that compound, reacting it with oxygen, and then measuring the amount of carbon dioxide and water that forms. And that's because if you take a compound like this, some compound CXHY, I don't know its empirical formula to start off with. If you take that compound and combine it with oxygen, and this is true of any organic compound, we call it organic because organic means basically composed of carbon and hydrogen, and you combine that with oxygen with some heat, or we call that burn it, right? Then the products are carbon dioxide and water, all right? And the neat thing about this is the amount of carbon dioxide relates to the amount of carbon that you had into your empirical formula or your chemical to start with, because all of the carbon here was from here, and the same thing is true of the water. All of the hydrogen here ended up on your water, right? So if I can measure the amount of carbon dioxide, I can know how much carbon I must have started with. If I can measure the amount of water, I can know how much hydrogen I must have started with. And if I know the amount of carbon and the amount of hydrogen, then I can get the empirical formula, right? So this is a kind of a schematic of how this sort of thing is done, a little picture, a little cartoon here. Your organic compound is placed in here. Oxygen is flowed this direction. We burn it in the presence of the oxygen. Fancy word for burn of our burning organic compounds is combustion, all right? Combining it with oxygen to produce carbon dioxide and water. So we combust it. The products flow through here in their gaseous phase. Water is gaseous because it's nice and warm, right? It'll cool down and it'll condense, but it'll all be absorbed in this region, whereas the carbon dioxide will be absorbed by a different material. And then you can take these individual, what we call U-tubes here, and we can weigh them before and after the reaction and know the mass of carbon dioxide and the mass of water that came from this process. And there are other ways of determining other elements as well, for example, oxygen or sulfur, that sort of thing, but we won't get into that in this class, okay? So, if we do want to find out how much oxygen or sulfur or a third element besides carbon and hydrogen, what we can do is we can look at the, after we get the grams of carbon and grams of hydrogen, we can look at the difference between the grams of the sample and the grams of carbon and hydrogen and know that that mass must have been due to whatever was left. For the case here, they're saying oxygen might be another thing in your compound. So here's an example problem, okay? We have a 5.217 gram sample of a compound that contains carbon, hydrogen, and oxygen, and we combust it, and we get this mass of carbon dioxide and that mass of water, and now we're supposed to get the empirical formula, okay? Well, how are we going to get the empirical formula from this information? Here's what we're going to do. Again, we want, I don't know, do you remember what we want here?
No, I don't know what we're looking for.
Well, just take a deep breath and read the problem and find out what we're after.
It says we want the empirical formula, but I'm not sure what that means.
Well, remember, the empirical formula is just the molar ratio of our, in this case, carbon, hydrogen, and oxygen, right? So I'm after CXHYOZ. I just need to know what X, Y, and Z are in this chemical formula, right? That's the empirical formula. And I need these, what, in grams or moles?
Moles, if you want to get the empirical formula.
That's right, because those are not grams, they're moles. So I want moles of carbon. I want moles of hydrogen, right? So let's start with those two there. How are we going to get moles of carbon?
I don't know.
Well, what did we say in our chemical formula that we drew just a second ago with carbon dioxide and water? What did we say related to the moles of carbon?
Was it the carbon dioxide?
That's right. The carbon dioxide came from the carbon in the initial compound being burned. So if we start with the 4.512 grams of carbon dioxide, okay, and then we can go from grams of carbon dioxide to, and we're going to go to moles, because when we know moles of carbon dioxide, we know how many moles of carbon there must have been. So I can go moles of carbon dioxide, and from moles of carbon dioxide, I go to moles of carbon. And there I am. I'm already there. I'm already in moles of carbon. So hopefully you are getting used to this sort of thing.
Yep, that's 44 grams.
Now, for the people who are a little behind, where did you get that 44 grams?
That's the molar mass of carbon dioxide. You take one carbon, two oxygens, the mass on the periodic table, add them together. That gives us our 44 grams.
Very good. That's how many grams you need to get a mole. Excellent. So here I'm going to get the moles of hydrogen, what do I have to do?
Do you start with grams of water?
That's right. This isn't 4.512. This is 7.406. Sorry about that. 4.512 grams of water here. 7.406.
Oh, yeah, I see. Sorry about that.
Yeah, I didn't pay close attention there. We're looking at 7.406 grams of carbon dioxide here. Excellent, but the 4.512 goes with grams of water, and then I can go from grams of water, where do I want to go?
Moles of water, I guess.
Why do we want to always go to moles?
I don't know.
Because then we can use the stoichiometry, the mole ratio of moles of water here to moles of hydrogen in the initial compound that we started with. Okay? So, do we know how many moles of carbon there are in a mole of carbon dioxide?
Not really.
Well, let's think about it. Here's carbon dioxide. If I have 1 mole of that, how many moles of carbon?
Oh, that's just one.
Yeah, so 1 to 1 there. Very good. How about this one down here? Let's look at this one. How many grams per mole of water?
That's 18. I remember that from my homework.
18 grams per mole. Good. How about moles of hydrogen per mole of water?
Is that 1 to 1?
Well, look at water, H2.
Oh, it's 2 to 1.
Yes, 2 to 1. Very good. 2 to 1. Okay, so to get the moles of carbon. I take the 7.406 divided by, what am I dividing by? Oh, I missed it. 7.406 divided by 44, and that's it right there. 1.168 moles of carbon. And to get the moles of hydrogen, the 4.512 divided by the 18 times 2. Okay, very good. So we got 0.501 moles of hydrogen. All right, so now I got two of my values, 0.168 and 0.501. And I can write that down for myself up here. C, 0.168, and H, 0.501. Okay, now where do I get the oxygen from? Where do I get the oxygen from? Well, we talked about it briefly before, but what we're going to do to get the oxygen is we're going to get the grams of sample and subtract the grams of carbon and the grams of hydrogen. And the result will be the grams of oxygen. All right, so take the grams of sample, and from that subtract the grams of carbon, and then subtract the grams of hydrogen, and then we'll get grams of oxygen. Okay, so grams of sample, 5.217 grams of carbon.
Do we know how many grams of carbon?
No, we don't, but we do know how many moles of carbon, 0.168. Does that help me?
Well, I guess we can convert it back to grams.
Yeah, that's right. That's what we have to do. We have to go to grams of carbon. So there's 12 grams of carbon for every mole of carbon, right? Moles cancel out. So 0.168 times 12. That is 2.016. So that is 0.016. That's how many grams of carbon. And then I also subtract the grams of hydrogen, which our moles of hydrogen was 0.501 moles of hydrogen. So that's going to be just a 1-to-1 ratio because there's 1 gram per mole for hydrogen. So 0.501. So 5.217. Subtracting the 2.016. And then I subtract the 0.501. So I got 3. All right, so then, whoops, gotta scroll back here a little bit. Then we take the mass of our sample minus our grams of carbon and grams of oxygen. And so that ends up being 2.7 grams of oxygen. So what I have so far, remind ourselves, carbon, 0.168, that's how many moles. Hydrogen, 0.501, that's how many moles. Oxygen, do I know how many moles of oxygen?
Yeah, you just got 2.7.
2.7? Can I use the 2.7 down here?
Yeah.
I can't though. Why not?
Why not?
Oh, because this is in grams?
Oh, yeah. So you got to convert that to moles as well.
Very good. So 16 grams for every 1 mole. So 2.7 divided by my 16, that is 0.168 as well, just like the carbon, 0.168. All right, so now pretty close. I just have to divide these out. It's going to give me carbon. I can divide it by the what? How do I divide it? Or how do I get this to the simplest whole number ratio?
Divide them all by the smallest.
That's right, so 0.168. So I get C1, H, what happens if you divide 0.5?
That's 3.
Okay, and then 0.168?
That's 1.
So C1, H3O. Okay, very good. So we got our grams of carbon, our grams of hydrogen from the moles of carbon dioxide and grams of carbon dioxide and the grams of water. And then we got our grams of oxygen by taking the sample and subtracting the grams of the carbon and the hydrogen. And then from that we got our moles of oxygen and found our simplest empirical formula, the whole number ratio in moles. Okay, very good. All right, so here's one for you folks at home. Let's have you guys go try to solve this one. Push pause and then come back and we'll see what you get. Okay, make sure you gave it a good effort. And if you didn't give it a good effort, go back and watch how we did the last one and then try to figure out this one, okay? But let's work on this one together. You ready, Fred?
Yeah, I don't really know how to do this one.
You don't know how to do this one? We just did it.
Oh, but I don't know how to do it.
Oh, okay, well then let's just take it one step at a time. Okay, so what do we want to the right of our equal sign, Fred?
That's the problem. I don't know.
Okay, so we're looking for the empirical formula. So what does that mean?
Oh, you want the moles then, huh?
That's right. We want moles of carbon, moles of hydrogen, and eventually moles of sulfur. In this case, this is that's the third element in there, right?
Yeah.
Okay, so how do I get these?
Well, moles of carbon you get from grams of carbon dioxide.
Very good. Grams of carbon dioxide to moles of carbon dioxide, and then moles of carbon dioxide to moles of carbon, right?
Yeah.
Okay. Where do I get the moles of water?
Grams of water.
Sorry, moles of hydrogen. Where do I get the moles of hydrogen?
Grams of water.
That's right. Grams of water. So then I go grams of water to moles of water, and then moles of water to moles of hydrogen. How many moles of hydrogen are there per mole of water?
That's 2 to 1.
That's right. And this ratio up here?
1 to 1.
Right? And then this is our 44 grams of carbon dioxide for every mole. This is 18 grams for every mole. Very good. So then I'm going to get moles of carbon and moles of hydrogen. 9.377 grams of carbon dioxide, 1.59 grams of water. All right. Let's do that in the calculator. 0.213. .177, and then moles of sulfur. Where do I get moles of sulfur?
I don't remember that.
Okay, well, what we have to do for moles of sulfur is, like the last problem where we looked for moles of oxygen, first we have to get grams of sulfur from and then we'll go from grams of sulfur to moles of sulfur. But we get grams of sulfur from the grams of sample minus the grams of carbon and the grams of hydrogen. And the rest must be the grams of sulfur. So it told us how many grams in the sample?
3.88.
All right, and grams of carbon, how much do we have?
0.213.
You mean this value over here?
Yeah.
But that's not grams, is it?
Oh, no, that's moles. So multiply that by 12.
All right, so 0.213 times 12. That's 2.556. And grams of hydrogen, 0.177. How do I get, moles of hydrogen, 0.177. How do I get that to grams of hydrogen?
Multiply that just by 1.
That's right, 0.177. Again, we went from moles of hydrogen to grams of hydrogen, and there's 1 gram per mole. Here we went from moles of carbon to grams of carbon, 12 grams per mole. Okay, very good. So 3.88, subtracting the grams from the carbon, 2.556, and also subtracting the grams that are from the hydrogen there, I get 1.147 grams of, what is that?
Grams of sulfur.
That's right, 1.147 grams of sulfur. So 1.147, divide that by 32, because there's 32 grams per mole. I get 0.0358. 0.0358 moles of sulfur. So, if I have 0.0358 moles of sulfur, 0.213 moles of carbon, and 0.177 moles of hydrogen, then I can write myself a empirical formula, right? Let's see if we can write our empirical formula down here. C, 0.213, H, 0.177, S, 0.035. Okay? So after I got my empirical formula for my moles, what do I do now, Fred?
Convert those moles, well, divide them all by the smallest number.
Yeah, divide them all by the smallest number, 0.0358. Okay? So that gives me S1, H, .4.9, and 0.213 divided by 0.0358, 6. So C6, H5, S1. Oh, there it is. We got it. C6, H5, S1. Okay. Very good. Lots of work, but nice to know that we can get the empirical formula from this sort of information.